recent work. So as you can see, the title is String Charge Duality in a Context of Integrable Lattice Models. I think it's a nice title, especially because it's not really clear what it means, but hopefully I can explain this along this talk. So this work is, it's not published yet, but it's on arXiv, and it's been done in collaboration with Owen Quinn from Amsterdam, Jacopo Denarius is now in Coleman Mine in Paris, and Michael Brockman from Dresden. Okay, forward. So let me just first give you some, just a little bit of background and motivation for this work. Somehow the general context of this story, it's basically a very elementary question which one can ask in the context of statistical mechanics, namely to understand the role of thermalization and relaxation in many body systems. Of course, this topic has a very long tradition, and in classical dynamical systems, it's understood really to great level, and we have this ergodic theory and theory of chaos, which basically explains what are the circumstances which lead this classical dynamical systems, generic classical systems to thermalize. But more recently, in recent years, researchers began to focus on quantum many-body problems and try to understand what is the microscopic origin of thermalization in these problems. And it's been yeah, so there's many works. It's hard to sort of summarize in one sentence, but one of the main achievements was this Einstein thermalization hypothesis, which I believe was formalized by Mark Stringitsky already 20 years ago or so, which essentially just says that if you have eigenstates of a generic quantum many-body problem, which are very close in energy, then these eigenstates are basically, if you try to measure them with only local observers, so if you only have access to matrix elements of local observers, they will be very close to each other. And this basically allows, I mean, this justifies the use of thermal ensembles for expectation values of local quantities.
Just a comment. So none of these people ever spoke about local observables, as far as I know.
So David Deutsch, this is pretty on the general grounds, but I'm trying to just set up. Basically, locality is important in this context because you want to understand the role.
I know, but I mean, none of these people actually had this in mind. They were talking about suitable observables or whatever.
Okay, this is maybe well.
That's what I meant. Suitable meant local.
I suggest we just continue, since yeah, this is not really, it's just a sort of a gentle introduction to the topic, if maybe somebody is not really familiar with that. But yeah, so it's really, let's say this is to a great extent understood by now. So the questions which we want to address is, are there situations where thermalization does not occur, or it has to be modified in some sense? And one can say that, well, there are of course classes of problems like that, which one can sort of call non-ergodic phases of matter, and sort of different formats has to be developed in order to properly grasp the statistical properties of those problems. So I just wrote down 3 classes of these models. So obviously a very known class are non-interacting models, but essentially these non-interacting models, this is one particle physics, the dynamics is Gaussian, and so forth. So they're really special, very reminiscent of classical models, and which allows you really to basically explicitly address all these questions. So sort of they are like the easy problems. Then there's really, the question is, are there...
So once again, can I make a comment? I mean,
Sure.
I don't think this is true. Because first of all, the dynamics is not always Gaussian. You can start in an initial state which is not Gaussian.
Right, yeah, okay.
Yeah. And for example, if you study the Ising model, you quench from the ordered phase, initial state is not Gaussian.
So initial state can matter. So if you start with, of course, with a state...
So it's actually not true that this is always a simple matter at all. Yeah.
Okay.
Yeah, it can be simple, yeah, but in general, it's actually quite hard.
Yeah, so I agree with that comment. Thanks for that comment. I'm just trying to be more more vague, just to sort of. Yeah, so but essentially there is a really class of generally interacting models where sort of even for it's not really clear what should happen. I mean, a priori in the and one particular case which we're gonna talk about now is are integrable models in the context of Young and Baxter, so Young-Baxter integrability. And there are other possibilities, for instance, many-body recognition, which is a very hot topic right now. There are also some sort of effective conservation laws which are responsible for authorization of wave functions, which would also lead to sort of physics which deviates from predictions of canonical statistical ensembles. So today we're talking about Young-Baxter integrability. So to be more specific, the question we are interested in is if there is some invariant measure or ensemble, if you will, which describes a time average of local observables. So you consider some local observable A, and then you prepare your system in some initial, say, pure state. You evolve with time, and then you sample it across the time trajectory, and this should sort of, in this sense, this should converge to some value. And the question is, can this value be represented by integration over some suitable statistical ensemble? And the conjecture which has been put forward is the generalized Gibbs ensemble, which basically tells you that, okay, if you have these non-ergodic phases of matter, identify what are your conservation laws, which go beyond the energy, and then use this conservation law to construct a generalized Gibbs ensemble in this sense. So basically, it's an ensemble which it's a unique ensemble which obeys all the restrictions which come from conservation laws and is compliant with the maximal entropy principle. This justifies this form. And yeah, so the idea that this Q, which are now here just some formal objects, I'm not saying what they are, but this should be all the local conservation laws of your theory. So you can ask now, how about non-local conservation laws, which normally also exist? In principle, you could include them in this measure, but the situation we are interested in is really the thermodynamic limit, where your system is very large, so one can show that these conservation laws then only have subleading effects with respect to system size, and they will drop out in the thermodynamic limit. So it's really the local conservation laws that one needs to operate with. So yeah, the question is now how to test this conjecture on the level of really interacting many particle systems.
But also if you just take the free theory alone, not to talk about more complicated, sophisticated things, you immediately realize that the local are insufficient. You really have to rely on the non-local ones.
Yeah, so to my understanding, when you switch to non-interacting particles, you get many exceptional features which then you have to account for. So, for instance, you can have conservation laws which are profoundly different from ones which you get in interacting theories. And yeah, I don't know if it's by now really clear what are the proper local degrees of freedom, local conservation law, which needs to be accounted for. However, so it's really, this is what I'm trying to answer today. So really discussing the question what really locality means in quantum lattice models. So now I'm not trying to say that what I'm saying, what I will say today, it just applies to Young-Baxter integrable models, and more particularly lattice models. So field theories might have some special features we deviate from that, and non-interacting particles may also need to be
do you agree that essentially what you need is the mode occupation? Do you agree or not on this?
Yes, we will see that. This is some sort of, because even in interacting theories, there are well-defined quasi-particle excitation, thermodynamic limit, and you basically have to fix the momentum distribution function for that, something like that. But I'm coming there, yeah. Okay. So, but
always sufficient.
Yeah. So basically,
more,
yeah. So we can maybe postpone these topics for later on. So at the moment, yeah. So then, okay. So we deal with integrability as I said a couple of times. So there is, of course, this question, what is integrability, right? So here I'm not trying to define rigorously what integrability means. And this vague language, people normally say it's existence of a macroscopic number of additional conserved quantities. But of course, we all know that it's a trivial definition because any quantum mechanical system, you can diagonalize Hamiltonians, you can consider just operators which are projectors onto eigenspaces, and these are by construction conserved quantities. So this is not enough, that's clear. So normally then in literature you would read, yeah, what you require really is locality. Sort of locality saves you in the sense that you need to have of order n, when n is number of, say, particles in a chain, of order n many quantities which are of this form. So they can be expanded as sums, as homogeneous sum over some densities. And moreover, these densities are really some operators which live on a compact region of space. So really act on finite number of spins, if you will. So m is the number of spins where this quantity acts, for instance. And yeah, so then the question is, can one explicitly try to see if GG conjecture works? For instance, on the simple, really paradigmatic model of integrability, which is the Heisenberg spin-1/2 chain, by, say, just simply constructing all these quantities, so local conserved charges, and put them in this exponent and see if the predictions are valid. Of course, the obvious problem here is that you don't know how. So after you obtain this result, what to compare to. So in the sense that just a year or two ago, there were no exact steady-state descriptions available for this problem. So say this fits now in a context of quantum quench, for instance. You start with an initial state, you let your system evolve, and then you're interested in steady-state properties after a long time. So this was a very hard problem to solve because it required, in the first place, to understand how your initial state gets decomposed in terms of your eigenstates, and then use this information to construct really the asymptotic of your time evolution to determine your steady state. And but a year or two ago, there was this proposed this quench action method, which does precisely that. And so I will not explain now in details what this method is, but it allows you basically to use the explicit form of the overlaps between your initial state of your quench problem with eigenstates, and then construct a steady state description for that.
Can I just comment?
Sure.
There was also something before this. So
Before this?
Not just the first attempt to construct this stationary state. We consider the quantum transformative approach before the conjunction.
Okay, so I'm sorry if I left out some references. I just
just a comment.
It's annoying.
Why did you Oh, yeah, yeah. Oh, yeah, 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 yeah. Oh, yeah.
Even before it was.
Okay.
Yeah. Let's use it. So that's
That's okay. This one just don't touch it.
yeah. They should not move properly. Yeah. So if I may continue. So then, yeah, eventually these techniques allow to compute statistical prediction without resorting to General-Gibbs ensemble idea. But on the other hand, it also really enabled to test the prediction explicitly by using sort of the same tools where instead of using the information coming from the overlaps, you just use the information coming from the charges, in the sense that now you had your initial state, you calculated what are the expectation values that your charges give on this initial state, and use this restriction in your ensemble to see what it gives you for local correlation functions. The upshot was, I mean, the outcome of this was, that the prediction for general Gibbs ensembles and co-injection approach do not match. And this has been really explicitly shown on this near initial state. But of course, this shows that in a generic case, this doesn't work. Moreover, one interesting result was that the known local charges, which are now called ultra-local charges, will only determine the distributions of unbound states which are in the spectrum of your theory. So in generic quantum integrable models, in your spectrum you have you can partition your spectrum with respect to different particle types, particle species. I will come into that at some later point again. And this interpretation of these particles is like some sort of bound states of harmonic excitations. And this ultra-local charges, the one that are sort of given in textbooks, only fix you the distributions of unbound states, which means that it's essentially your statistical ensemble is not constrained enough to single out really expectation values of local observers in a unique manner. So there is really something else that needs to be accounted for to really fix these predictions. And so there's been numerous papers which reported this failure of GGE, so to speak. And then, of course, the natural question was, are there some additional hidden charges, conservation laws, which are sufficiently local, which need to be included in the general Gibbs ensemble description in order to fix that and to reconcile the prediction of GGE with co-injection method. And now we're basically entering into a realm of quasi-locality, which is basically this another form of locality, which I would argue it's the thing that we need to solve this story. But let me just give you some brief historical perspective on this. So how quasi-locality emerged for the first time was by essentially studying transport properties in the gapless phase of the Heisenberg anisotropic spin chain. It's been known that for a long time that this in this phase the quantum transport is anomalous, that the system is a ballistic conductor, which basically tells you that there have to be extra conservation laws which are responsible for this behavior. So this is a sort of if you have your spin chain and then you sort of put some voltage bias so that you induce some current, if you want your system to be ballistic conductor, it really means that it has to be able to remember about this initial condition, which was some state which supported current. Only in this case, you can have current which does not decay after a long time. So this was the story, and the idea was to explain this phenomenon by using conservation laws. And
let me point out that in a paper with Fabian and Milos, Pamphil, we probably, I don't want to say we were the first in absolute terms, but among the first to point out the importance of quasi-local charges.
No, but these were earlier, actually.
so
Okay,
I'm
but
talking
in any
about-
case, the way I was put is in a way that, I mean, identify what the problem is, because the local charges are kind of moments of a distribution. You want to reconstruct the distribution.
Yeah.
You can do or you cannot do it. So this depends. So in general, you need extra information to add, and these are the quasi-local charges as well. That you might get from the lattice as well.
But your charges aren't only for continuous.
Depends how
When
you
you
take
stay
the
in the
limit.
lattice, for example, that problem you had isn't there for free theories.
Depends on the convergence of how the moments scale, right?
So in the paper, by Fabian and Maurizio, didn't they like has this correspondence between local charges and the occupation number on if you stay on the lattice? I thought that the problem arose. You have a problem when you go to the continuum. So in here, it's staying on the lattice. So
I'm staying. Yeah, I'm trying to be stick with the simplest example and try to identify what are local charges or quasi-local or pseudo-local, or it's up to it's a little bit ambiguous language, but the idea is that one can say
Could you give some examples?
Yeah, I will give you
What
that.
does it say?
I'm getting there. I will
Yeah,
try to
exactly.
solve the quench problem for this Heisenberg spin chain by really identifying a complete set of local charges, or if you prefer quasi-local charges. And I will show really what they mean. So this is basically what I meant by the title of this talk, which is charge string duality.
Maybe one other comment. Maybe it's a bit sloppy to say that the ultra-local charges determine the unbound states on the spectrum, because they give you the same amount of information, which would give you the density of the unbound states. But they don't determine it, because it's a coupled system of integral equations, and if you know the
I know what you
charges,
mean, but in some sense they do that. So, I'm intentionally a little bit sloppy, because otherwise I need to use very mathematical
but
definitions.
it's
and
not that the ultra-local charges determine the unbound states. I think this is.
Yeah, so we can talk about that.
Yeah.
I have a comment to that, but
Let me add a little more comment, which might be, no, I mean, I think it's of general interest. Now, when people talk about locality, I mean, local means very specific point. Local means you can move one point to the other. Now, if you go to the lattice, just to say I'm on the safe side, it's like I'm saying I'm on the rational numbers, everything for me is rational, and I will work with that. Now, there are real numbers, which you can never cover by rational, okay? So, what I'm saying is that the importance of understanding locality in a broader sense, not just on the lattice, is really an important fact. You cannot be just diminished like this. So, for this reason, I'm saying one cannot just push away, quantum field theory and other things, continuous theory and other things. It's there, especially if you address locality. Locality means something very specific.
yeah, and this is precisely where I try to go. But I want to separate I can't answer the question and just give a fully universal definition of what locality is for whichever non-ergodic phase of matter you have in mind. So this is why I'd like to start with a model which it's easy, it's tractable, and see what is there, and then move to more complicated instances, more complicated symmetries, going to field limit, going to classical limit, to quasi-classical limit, to non-interacting limit, maybe something else. So in some sense, this is the first step. So, and I think it's now pretty much understood what it means in this step, and I'm trying to get there. So, but yeah, why I was saying this, so I just wanted to say that, I mean, historically, this idea that there might be extra local or quasi-local quantities, so quantities which go beyond this standard ultra-local charges that I mentioned before, this basically started from these works. And the weaker form of locality which was imposed there to solve a problem that I'm going to describe on the next slide was to use extensivity of this conserved quantity with respect to Hilbert-Schmidt norm. So you can construct, you can just basically look at lattice which has n many sides, and then you construct basically, you take Hilbert-Schmidt inner product and then you study this quantity. So it's a weighted trace over square of this charge. So the idea, if this grows with the system size, so if this is an extensive quantity, it will be important to for the steady-state properties of this particular setup. And it turns out that such a family of conservation laws can be indeed identified and constructed explicitly. Well, it's really a continuous family, so it's a one parametric family of operators. So to be more precise, the story is like this. So the idea is to, as I said, there is an anomalous anomalous transport properties associated to this gapless space in the spin chain. And this anomaly is shown by the finiteness of the so-called Drude weight. So you study the DC conductivity at zero frequency. In Kubo-linear response theory, this is expressed as a temporal autocorrelation function of your spin current. And formally, this is the quantity you're interested in. And then it's known from the literature, from Mazur and Suzuki, and already back in the 70s, that this quantity, while it might be hard to really compute analytically, it can be bounded from below by incorporating the information from conservation laws. Essentially, you have here an overlap of your spin current with your conservation laws, and this is just a normalization factor. So if you sum over all conservation laws and go into thermodynamic limit, this will give you the bound for the Drude weight. In case you grasp all the relevant conservation laws, in fact, this should be really an inequality over here. Okay. But the point here is that this construction only applies in the gapless regime and at root of unity values of your anisotropy. Moreover, in order to bound this D away from zero, the quantities that you need are really different, fundamentally different from ultra-local charges, the standard ones, because they have different properties. They transform differently under spin reversal transformation. So if you take these Z charges, these novel quasi-local charges, they are odd under spin reversal symmetry, whereas all the charges that are obtained in the standard manner from the fundamental transfer matrix will be even. So this shows you that there is no overlap between Z's and H. And moreover, if you just want to bound this, so this bound, so if you put H over here instead of Q, this will be trivially zero because the spin current has also the same, it also transforms negatively under this spin reversal. So what I'm trying to say is that you really need different conservation laws in order to solve this problem. Okay, so this was the story, as I said, for the quantum transport. So the question we have in mind now is this quantum quench, right, and failure of GGE, so to speak. There is also, it seems like some extra conservation laws which are sufficiently local are needed to fix this issue. And with a little bit of, let's say, experimental mathematics, one can actually see that these missing quantities are simply obtained from higher spin transfer matrices. So what you do, instead of taking your Lax operator, which is a local unit of every quantum integrable model, you extend it over the whole Hilbert space, and then you trace out the auxiliary space. This will give you some transfer matrix objects. So normally what you do, you take this auxiliary space, auxiliary degree of freedom, to be the fundamental particle, in which case you get the so-called fundamental transfer matrix. But in principle, you can take in the auxiliary channel, you can take even higher, some higher spin representations, and you still get the valid transfer matrices. And then it turns out that if you take, this is very, very much the same as for the fundamental transfer matrix, you take logarithmic derivatives of this object around some particular point, which is called the shift point in the literature, you will get some analytic objects which are conserved by construction. And the question is, are they local or non-local, or what they are? So again, you can just use this Hilbert-Schmidt extensivity condition and try to see what are the restrictions on this parameter. And it turns out that, yeah, so these quantities, if lambda is a real number, there are quasi-local, and they are linearly independent, which is very important, from the ultra-local ones, which are obtained in the same manner from expanding the fundamental transfer matrix. So the question is then, do these guys repair the GGE? And the answer is yes. In what sense? In the sense that now, including the constraints which come from these higher conservation laws, you can also fix the distributions of your bound states. So I told you before that before the bound states were sort of not really determined only by considering restriction from the ultra-local conservation law. So now you can also fix the bound states, and by doing this you fix essentially the entire particle content in your thermodynamic spectrum, and therefore this should and it does really determine the statistical properties of local observables. Okay, so far so good. I hope I convinced you this works. So of course there are certain more conceptual issues related to this story, but I will save this for the end if time permits. So there are obviously a couple of drawbacks regarding to this construction. So first of all, it seems a little bit ad hoc because one has to really postulate some good trial set of charges on which you try to impose this quasi-locality constraint and see which one of them are good ones and which one of them are not good. And it's a little bit, it's a little bit unsatisfactory because maybe somebody will give you another integrable model and then you have to again make this educative guess. So the idea is if one can formulate some really group theoretic derivation of quasi-locality, which would allow you then eventually to generalize the concept to models with higher rank symmetries. And moreover, one thing which is also a little bit unsatisfactory is that when you're trying to include all these constraints which come from this higher quasi-local conservation laws, you need to apply some iterative procedure which you have to inevitably truncate at some level. So of course, for practical purposes, if you're interested in numerical results which are valid up to given accuracy, this might be sufficient. But the question is also, is there maybe some initial state, some situation which would allow you to really represent your steady state solution in really a closed form analytic fashion? And I will show that indeed this is possible in some cases. Yeah, so basically there's some elementary things about integrability. I think I'll skip through that. So the whole point is that integrability is not merely some extra conservation laws, but it's really has a more deep and profound meaning and has a very solid group theoretic foundation. So the idea is, why not using this object, this language, to sort of try to answer our question, because this is really the elementary, the soul of the problem, so to speak. And I mean, I would say that integrability sort of can be really the nicest way to state what integrability is. Its ability to represent your equation of motion in a lax form. This applies in quantum setup, in field theories, classical quantums, or even for non-interacting particles. So it's a really universal definition. Then infinitely many conservation laws is just a corollary of this representation. And moreover, what is nice is that lax representation really is it's manifestly local, so it doesn't spoil the locality of local way of looking at things. So to go to this particular model, which I'm investigating right now, namely the Heisenberg spin chain, it turns out that from this lax matrix you can algebraically derive what the scattering matrix for the problem is. This scattering matrix is the object which it's basically used to derive the quantization condition for your quasi-momenta in your spin chain, and this provides you with the sort of good quantum numbers which characterize your eigenstates in the problem. So it's a really an elementary and essential piece of integrable theory. Another important fact is that we are only interested in the thermodynamic limit. So when you go to thermodynamic limit, it turns out that description of your spectra significantly simplifies. So what happens in particular that your quantum number, namely beta roots, start to form some regular patterns in the complex plane, which look like this. So there's some real number, and then there is a bunch of roots, so these are called beta roots, which are equidistantly displaced along the imaginary axis. This allows you basically to get rid of this roots on the imaginary axis and only use the center of these strings, which are just the real numbers. And it sort of allows you to compress the description. And because of this formation of strings, so this is a pretty standard thing in the integrability literature. It's basically the thermodynamic Bethe-Ansatz method, for instance, really operates on this level. So it's a well-known thing. So I will not go into too much detail what these are. The point is, as soon as you have strings, then you can consider them as a composed objects. You can associate scattering matrices to them, and then you have these auxiliary functions which appear as some kernels, as I'm showing in a moment. These functions are sort of derivatives of phase shifts when associated to a given string. And using these auxiliary functions, you can basically cast your Bethe equations in this form of in the thermodynamic limit in the form of integral equations, and these are known as string Bethe equations. So now our variables, instead of individual Bethe roots, are in fact analytic functions which represent densities of distinct string types which appear in your spectrum. So rho with subindex j will be a density corresponding to a particle of type j on the interval between lambda and lambda plus delta lambda in the rapidity space. And similarly, there is a complementary variable which is a whole density which describes sort of the density of missing strings. And this is your string Bethe equations. Now I will just for a moment jump to something seemingly unrelated, but then I will merge the two in the next transparency. So there is the very powerful language of quantum Hirota equation, which is formally just some system of bilinear difference relations for infinite set of variables Tj. It's also known as the T system in the literature, and it's of this form. Here I'm using some compact notation to represent parameter shifts. It turns out that it makes your notation a bit more compact and it's easy to calculate. So this is the relation. Now, what does that mean? So, I mean, mathematically, one can think of this equation just as a quantization formula, so quantum analog of Weil formula for classical representation, for characters of classical representations of Lie algebras. But more physically speaking, this is just basically a nice, convenient way of representing fusion rules for your particle content of your theory. So why is it relevant in our context? Because you remember on the previous slide I showed you strings, and strings are precisely bound states of elementary particles. And so now in this context we also have some objects which are also have this composite nature built within them. So of course now I'm using this notation T, which basically suggests that this Tj are just the higher spin transfer matrices that I showed you before. And this is indeed the case. So the higher spin transfer matrices represent a solution to this equation. But this is not the only solution to this equation, just one of many possible solutions. It's called the canonical solution. And and so this equation expresses a functional dependence of these objects. And this is, by the way, this was probably a major reason why people did not believe that this fused transfer matrices can be a solution to the story, can provide you with extra local conservation laws, simply because these are functionally related to the fundamental objects, so they can all be, once you know the fundamental object, you can just use this relation to construct other transfer matrices, and then they cannot provide you with extra information. This was the logic, which I'm going to argue it's not correct. And yeah, just as a teaser, this relation can be really, on an abstract level, can be regarded as an integrable classical discrete system on its own. And we're going to exploit this fact in a moment. So why I'm showing you this relation? Well, the idea is that if you have this quantum Hirota equation, and you are aware of the fact that it's an integrable system, then it should be possible to linearize it in some way, so to really find the Lax representation for it. And this is indeed possible, and you can do that with aid of an auxiliary operator, which is called the Q operator, the Baxter Q operator. And this operator really linearizes this equation, and combining Hirota equation with this condition basically results in one equation which is quite well known. It's called the Baxter-TQ equation, which is of this form. So now, if you have this Q operator available, what you can do is simply plug it back to your Hirota equation, and you are able to explicitly express higher spin transfer matrices in terms of a sum of ratios of these Q operators. And now, since all the objects in this story commute among themselves, so they can be regarded as matrices or basically, since they commute, they're essentially diagonal matrices, and then you can look at these equations on the operator level or on the level of their spectra. It doesn't matter. So basically, what I'm going to do in the following, I'm going to abuse a little bit notation and not making the explicit distinction between operators and in their eigenvalues. These are some functional relations which I'm deriving, and they always work on the level of matrices and on the level of eigenvalues. And this is now particularly handy because I can employ this property to really extract out the local charges of the theory. And
Sorry, in which sense this is an equation? I mean, because
this
you
one,
yeah, above.
this
I
one.
mean, I mean, this they have different indices. They mean there are some restriction of some.
So this is T1 is the fundamental transfer matrix. T0 is some scalar function. So basically, you have to provide T0 and T1, but this really follows from group theoretic consideration. So this is your input. And then there always exists a Q function which solves this equation. In fact, there can exist many solutions to this equation, but it's enough to have only one solution. So I'm gonna just tell you in a moment what this Q operator or Q function really is for this particular model.
What is Q? What is Q J?
Q. So you mean this?
Yes.
Yeah. So this is, if I go back, I'm using this compact notation.
Ah.
So if you have
Right.
something in the box in the superscript, it just means you're shifting parameters, which allows me to drop parameters from the formula. Otherwise, it gets very lengthy.
Plus and minus,
Plus.
and minus index, T plus, T minus is.
Yeah, and this plus without a box, it's really like plus with a box, so it's the same thing. Yeah, so this is, it's not that I invented this notation, it's a standard notation but, from some other community. Yeah, so now let's see what this equation tells us. Well, first of all, so what we're interested in now is basically, we want to go to the thermodynamic limit. Where is thermodynamic limit here? It's basically contained, all these objects depend explicitly on the system size. But what is important is that there is this function, which is the ratio of these scalar transfer matrices, which is power to the n, where n is the system size. And you can see basically that this function, it's precisely 1 if j and k indices coincide, whereas for other indices, it's below 1, which means that in the thermodynamic limit, all the terms but one from this drop out. So now I'm just expecting essentially infinite volume scaling of this equation. So all the terms but one drops out, and this allows me to derive the following equation. So if you study this ratio, which by the way can be expressed in terms of y functions, which are another important set of objects which appear in the theory of integrable models, you can see that this ratio will go in thermodynamic limit to identity operator. And why is that? Well, basically, you will have here q divided by q, and for the other term, you will have the same ratio of q's, but turned around, and this will be basically identity operator. With this property, you can immediately conclude that if you take the following object, so logarithmic derivative of higher spin transfer matrix, this is just some normalization, which is not important, but it's convenient because from here to keep it. This object is now some conserved operator, which is sort of local, appropriately local. So why is that? Well, basically, I'm not trying now to go back and resort to Hilbert-Schmidt extensivity or anything like that. I just want to say that this is a local object because its spectrum can be written really in terms of these string particles, which I mentioned before, and it's manifestly additive. So then you take this object, you go to thermodynamic limit, it essentially becomes equivalent to that. And then provided you are inside this physical strip, I argue this is a local conservation law of your problem. So it's some object, it depends on auxiliary spin index J, so this is a discrete label, and there is another continuous label, which should be taken from this physical strip. So it's some region in the complex plane. If you do that, then this is a valid local conservation law. So I'm going to show you this by essentially using the explicit, the known form of the spectra of Q operators and show you what these objects really are. So the Baxter's Q operator, let's think of simply the spin chain at the isotropic point where the things are simple. In this case, this operator is a polynomial in the spectral parameter, which has roots, whose roots are identified with beta roots. So it's a degree n polynomial with, should be degree m, it's a polynomial whose roots coincide with beta roots, which is, so now it's very convenient to have this object because it makes an immediate connection to the spectrum of your problem. So what we are doing now, we are trying to connect the spectra of our charges. We are trying to write the spectra of our charges in terms of distributions of strings. And going to thermodynamic limit, one can derive the following equation. So one can see that, so here the spectral parameter mu is missing, but a charge is basically given as a sum over convolutions of densities with respect to some kernel functions. And this can be compactly written in this way. X is G times rho k, where here Einstein convention is assumed. This G is basically a matrix green function of the problem and can be explicitly derived by from a logarithmic derivative of your scattering phase shifts in your theory, and ultimately can be expanded in terms of this A function. So really the fundamental kernels which appear in the context of thermodynamic Bethe ansatz. So these are all really the objects which are scattered around the literature. So
is it the same as a small jk or not?
This formula you know very well.
Yes, I know.
So this is just the spectrum of the fused transfer matrix. No?
yeah, so exactly. So this is not the fused transfer matrix, this is the charge associated to it. So there is this logarithmic derivative. But the point is this G is a green function and its matrix elements essentially represent bare charges for your theory. So it's a very nice relation. So as soon as somebody gives you a distribution of strings and then you know what this is, you can tell what the expectation values of charges are. And that's the idea that I'm trying to explore here. Of course, in an application that we have in mind, we want to find the inverse of this relation. We want to be able to basically, by fixing one particular state and evaluating all the expectation values of our charges with respect to this state, we would like to know what these densities are. So formally, we just need to invert this relation. And this can be done in the following way. You define some discrete D'Alembertian operator, which acts like this. So remember here these shifts, which I introduced earlier. And this is just some set of, a countable set of analytic functions inside the strip. So for these functions, I can define this box F operator, which is that. And using this operator, I can show that the box on G is just delta. So in this sense, G is just the green function for this discrete D'Alembertian. And then using this box, we finally arrived at our string charge duality, which is of this form. So now this is really the inverse of the relation of this relation. So X is G rho. We invert it, and now rho is box X. So provided you know what the values of local charges are, by local I mean local and quasi-local, I simply call them local now for simplicity. So provided you know what all these objects are, you can map them to distributions of all your particle types which live in your thermodynamic spectra. And in turn, if you know that, you unambiguously fix all the local correlation function. This is already known from, for instance, from the thermodynamic beta ansatz, that the local quantities only basically, so let me put it that way. These functions essentially parameterize your Hilbert space of reduced density operators. So they represent a full set of quantum numbers which are needed to unambiguously determine expectation values of local observers. And now we identified basically a set of charges which provide the same information. Yeah? So in this context, Rho's distributions are local, are inherently local objects and charges as well. And this is one-to-one correspondence between them. Which means that, yeah, knowing this, it's basically, then solving a quench problem, for instance, just reduced to a technical problem of finding what the expectation values of these charges are. And this basically solves the problem as far as only equilibrium steady states are considered. So, yeah, maybe one comment regarding to that. So, strings basically capture, so to speak, the particle content, the particle sector of your theory. There are situations where you could have steady states which go beyond that. And an example of that, I showed you a couple of slides before, were these extra conservation laws which are responsible for asymptotic currents. These extra conservation laws do not fit into this story. They cannot be obviously related to distributions of particle types. So I have to exclude these things, these extra situations. But yeah, so the Heisenberg, so this extra conservation laws which go outside of this box, these are really exceptional. So, so gapless phase in the Heisenberg spin chain is really an exceptional problem because of this extraordinary degeneracy which appears at root of unity deformations. And this basically explains why there might be extra conservation laws in this case, because really your symmetry gets larger. But apart from that, this should be basically a universal way to make a connection between the particle types in an integrable lattice model and the corresponding complete set of charges. Just very briefly, because I see I'm very long. So what I showed you before was all for, say, for the isotropic point. The question is now if one can sort of identify the charges, the complete set of charges also in the gapless, in the critical phase of the Heisenberg spin chain. And it turns out it's possible, but there are certain peculiarities which arise. But on a formal level, you still have this equation of the same type. So there is this matrix green function. It only acquires an additional quantum label, which is related to the existence of a string parity. So now strings can be attributed either positive or negative parity. This gives you an extra quantum label, which you have to incorporate in this description. But still, you have some sort of the Lambert equation, which relates density between and charges. The only difference is that now in the gapless phase, this is not really strictly the Lambertian, but it's a little bit modified. It has some non-local features in it, but I don't want to go into these technical points. But on really on a formal level, everything is still there. Okay, so yeah, this is basically one example, just maybe briefly. So if you see that one particular value of anisotropy in the gapless space, say where anisotropy in units of pi is 3/7, what you will see, then you open, say, Takahashi's book on thermodynamic beta ansatz, you will see that the string content, the number of distinct string types which appear at this value are strings which are labeled by quantum labels 1+. One refers to the string length, plus and minus refer to string parity. So you have string of length 1 with positive parity, string of length 2 with negative parity, and so forth. We have 5 different types of strings. And then the complete set of charges is given by this for this particular value. So you have 4 analytic families of charges, which are labeled by 1+, 2+, 4-, and 6+. So one obvious thing to ask here is, okay, now you said that there is one-to-one correspondence between strings and charges, but in this particular case, we see that there are 5 distinct strings, but only 4 distinct family of charges. So Is there some missing information? Yeah, it turns out that there is some peculiarity associated to two particular string types which appear at the end of this classification scheme, which are called the boundary pair of particles. And there are certain unresolved issues at the moment, really how to fix independently the distribution of these two. However, at least for the cases where your initial states are restricted to the sector with vanishing magnetization, one can show that the distributions which belong to these two boundary particle types, which I denote here by A and B, are really inversely related. So the density of A is related, it's precisely the holes of B. So say this is A particle, this is B, and vice versa. And by using this information, you can essentially plug everything back and really use this magnetization sum rule to show that everything is consistent in the sense that your magnetization density gets restored after integrating all particle distributions. But away from Hall filling, it's not really know what to do. So it seems that there are some maybe some extra features which arise which have to be accounted for. Yeah. Okay, so I think I'm skipping over this. So here I wanted just to point out what I mentioned earlier briefly, that Hirota equation by itself also admits different type of solution, not only the canonical solution in terms of fused transfer matrices, but also some other functions can in principle solve this equation. And what is interesting is that if you consider a quench problem, say from a particular state, which is say a product of spin singlets like this, so these dimerite states, and then you compute the steady state, which belongs to this initial state, then you can see that the steady state can be essentially parametrized, again in the form of a solution to the Hirota equation, in which case the T functions are of this form. So psi here is the dimerite state, and this set of functions, which are simply linear functions, basically solves you the problem. In what sense? So you have these T functions, then from them you compute Y functions, there is one-to-one correspondence. From Y functions you compute the density functions, it's again one-to-one correspondence, and from density functions, as I said, there is one-to-one correspondence to the charges. So you can move left and right along this diagram. And this is the solution for this particular state. Okay, this is one interesting remark. And finally, there is a couple of conceptual points I want to raise before I conclude this. So yeah, going back to the question, is the steady state after say a quantum quench really described by the generalist Gibson Sumner? Previously I said the answer is yes, but let's now be more careful and really think what does the result I show you really imply in this context. What I think it's important to say is that GGE has been introduced as an ensemble which is distinguished by maximal entropy reasoning. So essentially you fix all the relevant values of all the relevant charges, and then you're supposed to get sort of a manifold of states which are consistent with that, and then maximal entropy principle will single out you the form of this type. However, what turns out now is that if you have a genuine closed integrable model like the Heisenberg spin chain that we discussed, then essentially there is no room for entropy anymore, because your local symmetry completely constrains the distributions of your thermodynamic particle content, and therefore, in turn, all the correlation functions. So there is one unique set of density distributions which is precisely determined by specifying the value of the charges, and there is no room for additional sort of optimization of entropy. So this is one remark.
Sorry.
Yeah.
Here you are already assuming that it's a stationary state. So you're already maximizing the entropy. Because this is what you find also in non-interactive models. It's just fixed, but you are maximizing the entropy because it's not stationary.
For instance, this was in the original proposal for the GGE where only the ultra-local charges have been included. What happened is that you still have the infinitely many possibilities of...
Okay, but let's consider a simple model in which the local conservation laws are enough. the non-interactive models.
Yeah.
So you have a maximal entropy principle that works.
I'm going to comment on in what sense sort of the entropy enters the story in the point number 5. But according to me, so what is important? Really, let's be very how to say. The question you can say, okay, there is this form. Am I forced to use this form of an ensemble in order to solve my problem? The answer is no, right?
We know that the answer is no.
Yeah.
You don't need to, there are infinite remaining representation of the stationary state. It's just a choice, and it's a canonical choice, a grand canonical choice.
So I have to agree with Maurizio. I mean, so entropy does play a role. So you're fixing a macro state in the end of the day.
Yeah, which is macro state is basically state which captures local physics, and this is what was our initial question.
Your root density are smooth functions.
Yeah, sure.
So, and this is why you have a maximal entropy. Otherwise, you could allow for not functions. Just
But we can discuss this.
Let's discuss. So I have another point. So I'm just trying to basically compress what my point of view on this is, and then I'm really open to discuss about these matters. Yeah. So of course, if you adopt this way of thinking, then another question to address is, okay, what is the role of these numbers, namely the generalized chemical potentials? Do they have some physical meaning? And I argue that they don't have any obvious physical meaning, simply because there is no, say, distinguished discrete basis which basically parameterizes these generalized ensembles. But instead, what you need to do is to account for all local symmetries that are out there, in which case these numbers really have no meaning.
Okay, but so this has been known for a very long time.
Maybe. So I'm just trying to yeah, because sort of writing this form down, it suggests that there is some content in these numbers, right, Fabian? You would not agree? So if you write this down, say you want to explain to somebody what generalized Gibbs ensemble is, then the logic is really sort of trying to extend the grand canonical ensembles. You have temperature, chemical potential, which fixes the particle numbers, and then maybe something more. So if you write the form like that, you're sort of implicitly
You're assuming that the Q's are quantities that satisfy additivity, right? So that's what you use for the construction of canonical.
Precisely, yeah. But now we have a continuum of these quantities. And this makes sense because we want to fix, we want to fix a continuum, we want to fix some distributions, some set of distributions. So we need really infinitely many numbers to fix, in which case, what is the role of this? But we can discuss about this more after this talk. So, of course, related to that, the question, how many independent local charges are out there? So, initially, I think the belief was that there are order n when n is system size charges, which are sort of the moments of your logarithmic derivative of fundamental transfer matrix. So this is the standard construction. In this case, these charges were really ultra local, so they had densities which were compactly supported, and sort of some people argue that these are sort of the natural degrees of freedom to be sort of that this represent the physical degrees of freedom. But now, since we see that the spurious objects play an important role, of course, one can say now we have infinitely many families of these fused objects, say that we are at this isotropic point for simplicity. So the answer should be order n squared. But again, as I said before, what you need to prescribe at the end to fix your local observables is really a set of analytic functions. So then really in thermodynamic limit, it's a continuous information that you have to prescribe. Of course, what you can do here is to get this result, you should just maybe consider ultraviolet regularization of your rapidity space, and then you just sort of put your rapidity space on a lattice, and then you would recover something like that, and then you just study more finer and finer lattices. Yeah, so that's also one thing I'm really curious what's your take on this question. And yeah, so finally there is also this question which remember we started this story somehow by saying the generalized gist ensemble should provide you some redundant description about observables in your steady state. Because we knew from the beginning that if we are able to take a sum over all the eigenstates, we're always able to solve the problem, right? So this is how some people introduce this problem to me. So yeah, it's not, of course, you can always integrate over the whole beta eigenstates, but is there a more compressed way of basically grasping the same amount of information? And now we see that essentially not really, because string beta state is what matters, and these are really the entire basis for your reduced density matrices. So in the sense, yeah, you're accounting for everything. The only thing that happens is that some states get indistinguishable, which is why I have another point. So this is to me the role of entropy. So there are microstates which are indistinguishable locally from a bit among themselves. And all these microstates which are locally indistinguishable are macrostates. And this is the only thing that we are doing. This is where the compression of information happens. But in principle, we are still summing over all possible eigenstates. Just to conclude, in this context, the charges that I show you is just one convenient, manifestly local parameterization of this space of reduced density matrices. Yeah, and to conclude, just a couple of, just to point out a couple of basically advantages of this approach that I explained today. Yeah, so while one may argue that conceptually this did not bring anything new, in principle it's a valid objection. However, this nevertheless provides a different language to talk about the problems at hand. So it really provides a different basis in which maybe tackling this type of problems may be easier. What is important is that these charges are manifestly local, so, and then for a fairly large class of states, you can basically try to get local correlation functions out of them by simply relying on locality. This has not yet been done, but it's one viable option to explore. Then what is nice that it allows you, it unifies basically the construction for all quantum spin chains in the first place, including the possible supersymmetry. So it's a unified language, which then eventually someday might allow us to identify what are all relevant degrees of freedom, namely all the charges for the Fermi-Hubbard model, and tackle also this problem, which, as we all know, it's very difficult. And finally, it might be also useful to study relaxation toward equilibrium state. So really finite time physics by using it as a basis, and then try to incorporate some sort of excitations into this picture. So these are all things that can be explored from this point. But yeah, I think it was pretty long, but in principle, I will conclude with this. And yeah, thanks for your attention.
Okay, so we have had already quite a few questions, but if there are any pressing questions, you can ask right now. Otherwise, we postpone to.
Is there a physical picture for why including the high spin transfer matrices captures bound states?
Yeah, because sort of higher spin transfer matrices, it's a sort of.
Should I think of that as a complex of spins?
Basically, they contain the properties of composition of particles. Of course, now you can say, okay, in this transfer matrices, where they take this composition is on the auxiliary level, which you then take out. But still, the information about composition is then imprinted on your physical object at the end. So really, transfer matrix, which captures some information about how what the bound states in your spectrum are. If you take just the fundamental transfer matrix, it has it's built of a Lux matrix, which has a physical spin, which is 1/2, because it's a spin 1/2 chain, and there's another spin 1/2 particle. So you don't see basically, you don't have the information about composition of particles. This is why these extra objects are needed. So it's really like on the string side, strings as really this bound states of Magnus. Yeah, they're composite objects. They're really.
So does spinors get me information on 2s, up to 2s strings of size 2s. Is that how it works?
Yeah, so the point is that charge string correspondency that I show you is really a local relation. It relates the density of a particle of type J with the charges of type J and its neighbors. So it's not really ultra-local, but it's local. So information in the spin J transfer matrices is related to information is J of J strings.
Okay, so I think we leave it there, and let's thank Enej again.